looking on YouTube and I saw this video talking about Mother's Little Helper. It's a Rolling Stones song from the 1960s. And it immediately brings to mind a very specific chemical compound, and that chemical compound is called diazepam. The song is referring to, and the lyrics in that song are referring to a little yellow pill, and that little yellow pill is a drug called Valium. And it was a very widely prescribed, and still is one of the most widely prescribed drugs in the world. It treats anxiety, so you know, if you're filled with stress or whatever, you take a Valium and just like, everything is good, and you fall asleep, and of course you wake up, all the problems are still there. But it's wildly successful and still wildly popular today. Let's go ahead and take a look at this molecule, diazepam, that is marketed under the trade name Valium, kind of like you market cola under the trade name Coke or Pepsi. So what's interesting about Valium and makes it relevant for today's lecture is that Valium contains a functional group called an imine. It's a CN double bond, and that's what we're going to talk about today. It's one of the 5 recipes I said you really have to learn for this chapter. So it activates GABA-A ion channels, those are depressive neuronal signaling pathways. And the last step in the synthesis of Valium involves taking 2 reactions that simultaneously occur, not simultaneously mechanistically, but they happen in the same pot. One of the reactions is an SN2 substitution, where you substitute the chlorine atom with ammonia, using ammonia as a nucleophile. So that makes this carbon-nitrogen bond here. But then in the second step, this condenses. It condenses to lose water. I'll draw the water byproduct. That's not at all interesting. But it condenses to form a CN double bond. And that's really one of the themes of this chapter, is condensing nucleophiles with carbonyl groups in order to give off some sort of water or a byproduct that contains the equivalent of water. And so when you take diazepam, you're actually taking an imine molecule as a drug. Now, we don't know the actual order of those steps. Is the first step the SN2, or is the first step the imine followed by an SN2? That's not really that important. Bottom line is that the last transformation that you do in a flask is this combination SN2 and imine forming reaction. I noticed my iPad is down to 24%, so we'll see how that works. I forgot to charge my iPad. Okay, when we left off, what did we talk about? On Friday, we talked about cyanohydrins, and which is really not a condensation because you don't give off water as a byproduct. You add HCN across a carbonyl group to form a CC bond. And then we talked about this carbon-carbon bond forming process called a Wittig reaction, where you can take a carbonyl group and then convert that into a CC double bond with one step using a single reagent, this thing called a Wittig reagent, which we sometimes drew in this ylid form, P plus C minus, which should seem very unfamiliar to you. But I told you that we're going to often will represent that with a double bond, just because when you're drawing out molecules using our standard drawing programs, it's just easier to write the double bond than all those pluses and minuses. They are the same molecule, they're just different representations, different resonance representations of the same functional group, this phosphonium ylid. But the key is that it's nucleophilic on carbon. That's the key. And that's why it's helpful to draw it as P plus C minus. You remember it's the carbon that's the nucleophile. Now, I told you how to synthesize phosphonium ylid reagents. First step is an SN2 reaction to make a phosphorus-carbon bond. You end up with P plus. And then you deprotonate it next door using a crazy base nucleophile, butyllithium, right? We spent the previous chapter using butyllithium and alkylithiums as nucleophiles for carbonyl groups. That's exactly right. They are nucleophiles for carbonyl groups. But if you have no carbonyl groups in your reaction and you have a phosphonium salt, you can deprotonate. And this is the only way we will teach you for how to deprotonate phosphonium salts to make phosphonium ylids. Now, you've got to be careful with how you make CC double bonds, and I want to talk about strategically. Well, actually, let's go through the mechanism for this reaction. And then we'll talk about strategically how would you use the Wittig reaction to get around problems. So Let me go ahead and start off with just a simple molecule. I'll take an example where we have just a simple ketone. This is called benzophenone. Diphenyl ketone is called benzophenone. And if I line this up with our phosphonium ylide reagent, and I'm being very careful to align the P with the O and the C with the carbonyl group, the C minus with the carbonyl group. So let's go ahead and write this out. I told you before, I used to get confused about, P and P, like one of the P's is a phosphorus atom, the other P is part of the abbreviation phenyl, and you have to keep those straight. This is a phosphorus atom with 3 phenyl groups on it. So you can't write P3PH or you've got the wrong structure. You just missed it. You've misunderstood what the chemical structure is. Okay, so let me write this out in the ylide form. P plus C minus. I love that because it allows me to remember that the carbon is a nucleophile. But you could do arrow pushing with the other resonance structure. It doesn't have that nice C minus there. Now, as we draw the arrow pushing, you could never have guessed this, but the mechanism involves attack at the carbonyl. And if you've been paying attention for the last chapter, you should want to push those electrons to the oxygen. But we know through immense and detailed study that as the electrons build up on the oxygen starts to attack the P+. And you've never seen any mechanism like this before. The transition state is a 4-membered transition state with long bonds because it's a phosphorus atom. But you've never seen a mechanism like that before where you form this kind of square-shaped intermediate. It might resemble a little bit hydroboration oxidation, but that doesn't give you a 4-membered ring. So if I draw out this intermediate, it's going to start to look crazy as soon as I draw that phosphorus atom. Here's that phosphorus atom. And how many things are attached to that phosphorus atom? There's a CH2 in the lower corner of this 4-membered ring. There's 5 bonds to that phosphorus. And your brain is going to be going crazy saying, whoa, that's too many bonds. No, it's not. DNA, phosphoryl groups, protein kinases, phosphoryl groups, 5 bonds to phosphorus. That's not some big deal for us to have 5 bonds to phosphorus. Now, we started off with this very strong C double bond O. Carbonyl groups are a strong functional group. They're usually a driving force in organic chemistry, but a P double bond O is stronger. Now we're going to cleave this ring open and release 2 molecules, and there's a couple of ways I could push these arrows, but I'm going to prefer this way. I'm going to break this carbon-oxygen bond right here. You've learned about doing SN1 reactions of tertiary alcohols and things like that. So maybe this should look a little bit familiar, but we're going to use the electrons in this bond to attack the phosphorus and make a wildly stable C double bond O. And at the same time that is happening, I'm going to take these electrons here, and I'm going to choose, in this case, to depict it as ending in the middle of that bond to show that I form a CC double bond. Or you could make those the electrons in this bond here attack this carbon, but as long as you're precise, you'll see me do those types of arrow pushings both ways. So I'm going to get 2 double bonds here. So one of these double bonds look like this, and P double bond O is an incredibly stable bond. Boy, that's a stable bond. That's why DNA and RNA are made out of phosphoryl groups. The P double bond O is a stable bond type. And then we get over here, we end up with a CC double bond. So we start off, I'll draw the CH2 group there. So we start off with a C double bond O, and we end up with a C double bond C. And that's a powerful 1-step transformation. Once you have an alkene like this, think of all the reactions you can do. You can add HBr across that, and then you're ready to make Grignard reagents. You could do hydroboration oxidation, you could do hydration, right? The dihydroxylation with osmium. Remember that reaction from way back in chapter 14, I think it was? Okay, so that's a powerful process. Now, there's something important to remember about the Wittig reaction. Like this chapter, it is for aldehydes and ketones. It is not for esters. Do not try to take this reaction and apply it and apply the reaction to esters. Even though esters and amides, either, you can't do amides, they both have carbonyls, but these won't undergo this reaction. So if I take an ester like this and I throw in 50 equivalents, 1,000 equivalents of this Wittig reagent is not going to react. So you won't get, I'll just write this in red. Well, how do I do this? I don't want to use red. I'll use a dashed line here just to indicate that it doesn't happen. No. There we go. So don't try to do the carbonyls of esters or amides. This chapter is about ketones and aldehydes. This reaction only works with ketones and aldehydes. All right, so how do you take advantage of this new reaction for converting carbonyl groups directly into alkenes? You already know how to make alkenes. Remember all this E1 and E2 and all that stuff to make alkenes that never quite seem to be useful or seem to make sense? Let's suppose I give you this and I say you can make it from some six-membered ring compound, right? Strategically, how would you approach this? Now, this is different from the kinds of problems that I give you on my exams and on my discussion section worksheets. I always tell you the starting materials. I say, here's the starting materials. You figure out a way to make this. But let's go ahead and talk about strategically, like how would you make this kind of a tri-substituted olefin that you see here, this CC double bond, right? I'll go ahead and start off by talking about the classical way that you might have tried to make this using chemistry from previous chapters. Let's suppose I take carbonyl groups, right, a CC double bond. You need to make a carbon-carbon bond in some way. So let's suppose I try to just add an alkylithium or a Grignard reagent to this. You should be well practiced with that because the last chapter was all about that. So step 1, I'll add ethyl lithium to this. Step 2, we're going to do a water workup. You should know that. Or you could use ethyl magnesium chloride or ethyl magnesium bromide. Those are all going to work here in the same way. And that allows us to make a carbon-carbon bond. But unfortunately, we've got this OH group that we don't want, because I told you how would you make an alkene, not an alcohol and a CC bond. Now, you know how to convert alcohols into double bonds. You take sulfuric acid, and it dehydrates alcohols, especially tertiary alcohols that form stable carbocations. The problem is with this is that once you form a stable carbocation here at this center, you can't control whether you deprotonate from the ring or from this ethyl group that's sticking off the side. You can pull protons off of all of those sides, and so you'll end up with a horrible mixture of two compounds that you cannot separate. The boiling points are similar. The physical properties of these two compounds are similar. Nobody wants to generate a mixture. I ask you how to make things efficiently on my exams. That's one of the key words I put on my problems. And this is not efficient if you generate this mixture. So this is where the Wittig reaction really becomes useful, is in a case like this, right? If you really wanted to make this, and now you know this Wittig reaction, we only need one single Wittig reagent to make this happen. And this time I'm going to draw it out in the Wittig reagent in the resonance structure. So triphenyl, 3 phenols, put the 3 after the phenyl, phosphorus. And here I'm just going to draw the double bond resonance structure for that Wittig reagent. There's the Wittig reagent, and there we go. And I'm not going to draw the phosphine oxide byproduct, the P double bond O byproduct here. We throw away. Nobody cares about that. Okay, so you have to be, this really helps you get around a problem with dehydration reactions where you don't have regio control, good regio control, oftentimes for dehydration reactions. All right, there's another way you could have made this through a Wittig reaction in theory, and I want to talk about why this alternative way, because the book is big on getting you to recognize the limitations of the Wittig reaction. I don't know why they teach you the Wittig reaction and then they fess up and say it's all full of all kinds of limitations. But let me show you a different approach. You could have made that cyclohexane ring, in theory, into a Wittig reagent. Right? Maybe this is the Wittig reagent we wanted. And you could have had the carbonyl on the other ethyl compound, the 2-carbon compound. So we could have made this very efficiently through this Wittig reaction where the carbonyl was on the other side of the double bond. Now the problem is there's not an easy way to efficiently make this 6-membered ring Wittig reagent. And let me talk about where the pitfall is there. So the way you would make this, the last step in making this Wittig reagent is to do a deprotonation. So we must, if we made that Wittig reagent, we must have at some point had this phosphonium salt. And there's an H, or I'll draw the H, but we normally don't draw the H's. And the counterion doesn't matter. I'm just going to say iodide here. because I'm kind of thinking ahead. How would I get my hands on that Wittig reagent? And this is the problem. It's not easy to get this Wittig reagent efficiently. And the reason is the only way we've taught you for how to make Wittig phosphonium salts is through SN2 reactions. And even if we put the best leaving group that we can think of right now, which is an iodide, phosphonium, these phosphines are not that nucleophilic. And so this is not a good SN2, right? SN2 with triphenylphosphine is good for primary alkyl halides. Right? Secondary, lame. Tertiary, no, it's not going to do some SN1 thing. We need primary alkyl halide. So I'm going to write not primary here. To really, it's not going to be efficient. Not primary RX. So that's the problem. So, okay, but the Wittig reaction is commonly used in synthesis or variants of the Wittig reaction to make CC double bonds. In the Chem 51LC laboratory, you're going to be using a variant of the Wittig reaction. I think it's called the Horner imines. I forget which version. There's many different variations of the Wittig reaction. You're going to be using a variation in the Chemistry 51LC lab. All right, Valium. How do they do? What's with that Valium thing? Let's go ahead and talk about this imine forming reaction, how to make imines. So if I take here's our recipe for making imines. You take an amine with 2 H's on there. See those 2 H's? Let me highlight those because you'll forget. That's the key here. There's 2 H's. We call this a primary amine. We're going to have a whole chapter on amines. It's an amine that has 1 carbon substituent, 1 alkyl substituent, not a carbonyl, 1 carbon substituent, and 2 H's. Those 2 H's are the key. And the other piece is an aldehyde or a ketone. I'll do an aldehyde in this case. And we have this secret catalyst, catalytic acetic acid. I'll draw out the chemical structure so you can see. Oftentimes, I'll show you below, I draw that out using a text form. Okay, so that we have a catalyst in there, an acid catalyst. We don't want to add 1 equivalent of hydrochloric acid. That'll just protonate the amine. We need a weak acid here, not a powerful mineral acid like sulfuric acid. Right? We don't want to protonate the amine. We just want to catalyze the reaction, which goes through a complex mechanism. And the product of this reaction has this, where you used to have an aldehyde carbonyl or a ketone carbonyl, we now have a CN double bond. So that's the reaction. And the byproduct of this reaction is not interesting. It's water. We oftentimes add dehydrating reagents, powders and stuff to our reactions to soak up the water because we want to drive the equilibrium towards the imine. And this is exactly what was going on with that Valium thing, right? The Valium thing is a 7-membered ring. You're not good at drawing 7-membered rings, but I am. So I'll go ahead and draw out this. This is what the Valium thing was. This is. They didn't add catalytic acetic acid. They had special conditions. It had acid in their conditions. Okay, so that's how you make imines. Imines are valuable. You find them in drugs. You certainly find them in biological molecules. You might have heard the word Schiff bases. Whenever organic chemists hear the word Schiff base, we laugh because it's an archaic term, kind of like, oh, let me take my horseless carriage to the merchant store or something. Nobody uses the word Schiff base anymore. Okay, so let's go ahead and take a look at another one because it's not just aldehydes that are for this reaction. Uh-oh, let me switch over to my black pen so I get this high contrast here. And I'll have an amine, and look at those 2 H's on that amine. That's the recipe there for making an imine. And what's my acid catalyst going to be? It's going to be acetic acid. Now, we've got a lot of different ways. I think the book likes to write CH3. You don't have to write cat there. I just like to make it clear we're not trying to do some SN2 reaction using the oxygen atoms of acetic acid. But I won't require you to write catalytic. So here's another way to represent unambiguously acetic acid. The book might use CH3COOH. And if you go to any organic chemist, we would abbreviate that using ACOH. Acetyl attached to an OH. That is unambiguous. It means acetic acid. We tend to be try to be very economical with space when organic chemists write out reactions. Oh, great. This is going to make a CN double bond. It's going to make an imine. And so let's go ahead and draw out That imine product, where we used to have a ketone or an aldehyde carbonyl, we now have a CN double bond. And again, we've lost water. I'm not even going to draw the water byproduct. It has no carbon atoms in it, and you would simply evaporate that, or it would remove it somehow in your workup. Right, so we need to talk about the mechanism for this imine reaction, and it is laborious. It is a 6-step mechanism. We're going to have a bunch of 6-step mechanisms in this chapter, in chapter 20. There's some common themes here, although the order of the steps are not exactly the same, and so let's just get ready here. You've got to be able to draw 6-step mechanisms in this class, and this is the first one that you need to know. Okay, so the 6-step mechanism for the formation of imines. You know, I told you that there's some reagents where you keep protons and acids out of the reaction. Like alkylithium reagents. We don't have any protons that are potentially acidic, like alcohol or OH in those reactions. But here, we can have those types of protons present. But the conditions are weakly acidic. And the conditions are not so acidic that we protonate the carbonyl. The carbonyl has lone pairs on it. And you may be thinking, well, why would I protonate the carbonyl? Because chapter 20 is going to be full of you protonating the carbonyl. And you're going to get confused. At the end of this chapter, we're going to be protonating carbonyls, and you're going to get confused. Imines are nucleophilic enough. It's not like water. That nitrogen atom, like amines, are nucleophilic enough where they can attack the carbonyl at decent rates without the need to protonate the carbonyl. Right? You don't want to throw in a full equivalent of HCl because that would just protonate all your amine up. Okay, so we're going to generate a new bond. This is how we get that nitrogen-carbon bond going. So let me go ahead and draw out this next intermediate. And I'll draw those 2 H's on here because I've done this mechanism so many times. I know I'm eventually going to need those. So let me start drawing out those the amines. Now, I started off with 3 bonds to nitrogen. Now I have 4. You better put a plus charge on there. We're going to see plenty of these species called ammonium ions when we get to chapter 23, the amines chapter, and but for now, 4 bonds to phosphorus, you just put that plus there. And we pushed the electrons up to oxygen, so that better be O minus, and actually, you know, on my notes I had acetaldehyde with a methyl group attached to the carbonyl, but let me just keep going with the phenyl here. Okay, that's our intermediate. There's 4 bonds to that carbonyl carbon. Here's where our carbonyl carbon was. It's right there in the center. And now, this is where the acid comes into play. Now, I'm not going to draw the actual acidic species. There are lots of things that could, floating around in this reaction mixture, that could stick a proton on that O minus. This is the next step. Don't deprotonate the N plus. The conditions are slightly acidic. If the conditions are slightly acidic, we protonate the O minus before we use a basic species to deprotonate the N plus. So we're going to protonate that O minus. For gosh sakes, do not use that negative charge. Use the lone pairs. Electrons form bonds, not charges. Okay, so now we've protonated that O minus. And I'm glad I drew these bonds on the ammonium ion species because I'm going to need those. Now I could draw the that A minus up here, but I'm not going to do that because, again, I've done this mechanism enough to know that I need to deprotonate the N plus. So I'm going to draw the A minus at the bottom. And once you've drawn this a bunch of times, you'll remember, oh yeah, next step is deprotonate the ammonium ion, one of the H's. Let me draw that lone pair on my symbolic species A minus. We refer to that as the conjugate base. This is acidic condition, so we have, under acidic conditions, we have an acid, we have conjugate base. If it was basic conditions, I would have used HB and then B with a lone pair, but the conditions are acidic here. So how would I know whether the conditions are acidic or basic? Well, you look and see if you've added acid or base to the reaction, and if you can't tell, you can use either set of species that you want. HA and A minus, or HB and B, lone pair, B minus. All right, so we're 3 steps in. We're going to pull that proton off. We're almost 3 steps in. I'm going to pull the proton off of this ammonium ion. And that's going to lead us to this neutral species called a carbanolamine. I'm divided. In my notes, I wrote out the name carbanolamine, but for the life of me, I can't imagine why I would ever care if you know the name carbanolamine, so I'm not going to write it here. That's just going to, who cares whether you know that's called a carbanolamine? Right? I don't give multiple choice questions like, what is this called? Or some kind of question like that. Okay, that's called a carbanolamine, and it's now neutral. We still have HA floating around. We just regenerated HA. And this is critical for the reaction. So let me draw the HA. I'll draw it over here because I've done this mechanism so many times. Now, what's more basic, the lone pairs on nitrogen or the lone pairs on oxygen? The lone pairs on nitrogen are more basic. But if I protonate the nitrogen, I'm just going to go backwards to our previous intermediate. Sure, all these steps are reversible, and I could go backwards, but I'm going to try to go forwards and show how we get rid of this oxygen atom. All the steps are reversible. I'm not drawing reversible errors. I'm trying to show how we get to the imine product. So now, by protonating the OH, we're going to turn that OH into a water leaving group. And that's how we lose that oxygen atom from the carbonyl. And now, that lone pair on that nitrogen is really going to come in handy. I'll draw it down below because it's going to push out that OH2. Right? Each of these atoms on this carbanolamine intermediate, if I just kind of step back for a second and look at this carbanolamine, the O and the N are just waiting for the other one to get protonated. As soon as one of them gets protonated, it's going to get kicked out. So you protonate the N, you go backwards in this direction. You protonate the O, and you go in this direction. And this is true. We're going to see these species in this chapter where you have two oxygens attached to an sp3 carbon, nitrogen and oxygen, and those are really sensitive to acid. So now that we've protonated the O, we're going to push that O out. We're going to use the nitrogen lone pair. It's not like a regular SN1 reaction. This OH2 is getting pushed out. You can't stop that OH2 from getting pushed out by the nitrogen lone pair. It's the nitrogen lone pair. You can't get closer than being right next door. There's like it's not like an SN2 where you have to collide with two molecules and form a bond. There's no collision required. The nitrogen lone pair is there all the time, pushing, pushy, trying to push out that leaving group. And so now watch this. I'm going to draw a bond to this H on the nitrogen. Again, I've done this mechanism enough that I know I need that bond there, because the last step, we're going to deprotonate this species. This species is so important, I'm going to tell you the name, and I expect you to know the name. Not because I ask questions like, what's the name of this? But because sometimes I refer to these species. And when we get to the next functional group, the next recipe, I'm going to use this name again. And the name for this species is called an iminium ion. Iminium. Not ammonium, but iminium. Right? The neutral species is called an imine. The protonated version of the imine is called an iminium ion. That's an iminium ion. And we still have that A- that's been patiently waiting around here. Just patiently waiting to do something, and it's still there. We have to regenerate our catalysts. Let me draw the A- down here, and you can see what's going to happen. I'm simply going to deprotonate that iminium ion, and that's going to generate our imine functional group. Boy, that seems like a lot of work, doesn't it? A lot of arrow pushing, and you have to know this mechanism. You have to know this mechanism forward and back. If I ask you how to take, right, at the end of the reaction, you've got H2O, and we have an imine, and I ask you how to go backwards from an imine to an aldehyde, it will go through the same intermediates as I've drawn on this page. You just change the red arrows, but it's the same 6 intermediates, or I don't know how many intermediates. It's the same type of 6-step mechanism. It just goes backwards. Okay, so this is the 6-step mechanism for formation of imines. And remember, step 1, this is the hard thing to remember. Amines are nucleophilic enough to attack carbonyls, and you don't need to protonate the carbonyl. Later, with oxygen, you've got to protonate the carbonyl first. Oxygen nucleophiles. But amines are nucleophilic enough that you don't need to protonate the carbonyl. Okay, there's another reaction that looks so similar. when you look at the reagents. So similar to imine formation, but it's just subtly different, and that's enamines. So let's go ahead and take a look at the kind of neighboring reaction, the similar type of reaction, and that's enamine formation. So let's go ahead and take a look at enamines. Here's an example of an enamine. I'm going to go ahead and draw out a starting material. Is going to be an aldehyde or ketone. But critically, the thing that makes this reaction work is you have to have an H on the alpha carbon. Actually, let me go back. Let me draw this here. I'm sorry I drew pH. I should have drawn the benzene ring, the phenyl group. So you can see I'm tracing over that. The thing that makes this reaction work is that there is an H atom that I don't draw over here on that carbon next to the carbonyl. And without that H atom on that carbon next to the carbonyl, this reaction would not work. There's 3 H's on there, but we only need one of them. So the other part of the recipe that we need is an amine that only has 1 H. Now, if you had 2 H's on that amine, this would make an imine. But there's only 1 H. We're not going to be making any C double bond N that's stable out of this if there's only 1 H on the imine. So let's go ahead and draw out the product of this process. The product of this process and the conditions involve acetic acid again. I'm just going to write catalytic, ACOH. You could write CH3CO2H. You could draw the chemical structure of acetic acid as long as it is unambiguous. But if you choose to use this kind of lettering, don't write the wrong letters. It's capital A, lowercase c, acetyl group attached to OH. And the product of this reaction has a new double bond, but it's not a CN double bond, and this is what's wacky. The double bond is between the carbonyl carbon and the neighboring carbon. And we refer to that as an enamine functional group. That's an enamine. It's an alkene with an amine attached to it. And I think in this chapter, this is the hardest transformation to see, because the double bond in the product is not in the same place as the double bond that was there in the starting material. And you have to practice this to be able to see this. And you may think, oh yeah, I get the concept. No, you better work lots of problems, because it's going to seem, once we add functional groups all over the place, it's going to be hard to see what's going on. Let's take a look at another example. You know, this first reaction works and is selective because you can only form the alkene on one side. There wasn't any proton over here on the phenyl ring for us to deprotonate. So there was no way to make the alkene. You couldn't make the alkene go over here to the benzene ring. Otherwise, you would have had 5 bonds to carbon. So this is completely selective. There's no possible alternative alkene position in the product. Let me show you another example of an efficient imine or enamine forming reaction where there's one and only one product. And this is very common with cyclic amines, cyclic 5-membered amines. This one is called pyrrolidine. Like nicotine is a molecule that contains a pyrrolidine ring. 6-membered nitrogen-containing rings, like piperidine is the 6-membered version of this amine. Very common for this reaction. We need a catalyst. Guess what the catalyst is? It's the same. It's catalytic acetic acid. Just to be different, I'll write it out using a formula notation like the book likes to do. I think the book, I can't remember, I think the book likes to draw carboxylic acid like this, which spooks me. I hate that representation because students always think, oh, there's an OO bond in acetic acid. There's no OO bond in acetic acid. Right? I hate this representation. It's dumb. So I prefer the ACOH, acetyl group attached to OH. But I'm just showing you. It's like as long as you can represent acetic acid. Let's go ahead and draw out the enamine product here. Look, there's only one H on this nitrogen. So we're going to form an enamine, or we're not going to form anything. These are the only, right? So we're not going to form an imine out of this. We've got this new nitrogen carbon bond, and the CC double bond can be on either side. It actually, there's symmetry here, so it won't make a difference. We could put the CC double bond on this side, we could put the CC double bond on that side. They are the same molecule, won't make any difference. I'll put it over here to the right. There's a water byproduct here that I'm not drawing, right? You have to lose O and 2 H's. One of the H's comes from here. Whoops. One of the H's comes from here. One of the H's comes from this carbon next to the carbonyl, and the O comes from the carbonyl, H2O. And it's challenging because we don't draw H's on carbon, right? It's going to be challenging. Now, you can see how using acetone over here avoids this issue of which side do we take the H off of. You can see we pulled the H off of this side in order to generate a CH2 group here. But because our ketone was symmetrical, you get the same product regardless of which side you pulled the proton off of. So organic chemists don't like to generate mixtures of products. So we like to apply this reaction to symmetrical ketones because it doesn't matter which side you make the alkene on. It's the same product either way. Now we have to understand the mechanism for this reaction. The mechanism involves an amine, it involves an aldehyde or a ketone, and it involves acetic acid, and the first 5 steps are exactly the same as the imine thing. It's only the last step that's different, where we pull a proton off of a carbon atom instead of a nitrogen atom. And so let's walk through that 6-step mechanism again. It's kind of good practice for the imine thing, even though we're making an enamine. So let's go ahead and start that mechanism. So we have an amino group. We have a ketone here. I'm going to do acetone for this mechanism. There we go. And there's an acid floating around, but don't use the acid yet. Right? We just have a catalytic amount of acetic acid. And this amine is plenty nucleophilic enough to attack that carbonyl without protonating the carbonyl. And there are some nuances to this that you could go into more detail in a graduate level class, and we're not going through those nuances here. Okay, so this makes that nitrogen-carbon bond. I'm not going to tell you what the R group is. It could be phenyl. Whoa, what the heck? I've got the 2 in the wrong place. This is driving me insane. I'll just scratch it out with a black pen. Right? This would have given an imine. We want an enamine. 2 R groups on there. Boy, almost blew that. Okay, so we've attacked with our what's called a secondary amine that only has 1 H on there. So we're going to have this ammonium species, 4 bonds to nitrogen, positive charge. That's an ammonium ion. And I'm going to draw that NH. I'm sure I'll need that at some point in this mechanism. And I have this tetrahedral intermediate. Uh-oh, I better put that positive charge on the nitrogen. Don't forget that. And then I have an O- here. I'll circle the charge because it looks kind of like a oxygen-carbon bond if I don't circle. Sometimes I circle charges just so you know. No, that's not a methyl on that oxygen. It's a negative charge. So, well, now that looks like a theta symbol. Whatever. Okay, so we've got this species. We've got acidic... an acid catalyst present, and now here's where we use that acid catalyst in our mechanism. I'm going to use this O-, right? The conditions are acidic. You could deprotonate the N+ first if the conditions were basic, but this is running under acidic conditions, slightly acidic conditions, and so we protonate the O- first. And we're using this symbolic acidic species. There's lots of species floating around that could protonate that O-. It could be acetic acid, it could be an ammonium NH+. You don't know. So don't worry about it. Just write HA as a symbolic acid and don't worry about what's the actual species that's transferring a proton there. And I told you before that I've drawn out this mechanism so many times that I know I'm going to need to deprotonate this N+ in the next step. So I'm going to write the NH bond there, and I'm going to write the A- down below next to that NH+, because I've done this many times. I've practiced it many times. You need to practice it many times. The next step, it looks so obvious now because I'm drawing all the things in the right place. But when you're drawing it, and it's the exam, and you're panicked, and there's 1 minute and 27 seconds left, and you can't, right? You've got to practice this so you know how to do this. There we go. We're going to deprotonate that. And this gives us that neutral carbanolamine intermediate. Right? It's the same mechanism as imine formation. The same mechanism as forming an imine. And now we've regenerated our HA catalytic species, and so now we're going to protonate the OH. Don't protonate the N. Sure, that's happening, but we're trying to show how we get to the product, not the fact that nitrogen likes to be protonated. That's certainly true. We're trying to show how we get rid of this oxygen atom using an arrow pushing mechanism. So now we're going to deprotonate we're going to protonate the OH using the acid that turns the OH into a leaving group that is immediately going to be pushed out. It's not just going to leave, it's going to get pushed out. And I'll draw this lone pair here on nitrogen. That lone pair has just been waiting patiently now to push something out. Sitting there, lurking. As soon as that OH gets protonated, bye, goodbye. And so this takes us to our kind of key intermediate here that I told you the name of before. It's a nitrogen with 4 bonds, but 2 of those are part of a double bond. We call this, what is it called? It's called an iminium ion. Not an ammonium ion, but an iminium ion. I'm going to write the name here again because it's an important intermediate. It's an important intermediate in biochemistry. It's an important intermediate in chemistry. It's the key functional group that you find inside of retinal, rhodopsin, if you've taken biochemistry class, an iminium ion. Okay, now our last step, we've got to deprotonate something, but there's no H's on that N. We can't deprotonate N if it has no H's. It has 2 methyl groups, 2 methylene groups, 2 phenols, a phenyl and a methyl. Does not have an H. So if we're going to pull off a proton, it's going to have to be one of the protons on a neighboring carbon atom, like this one. Let me do it in black here. I could have drawn the proton on either of these 2 carbon atoms of acetone. And so now we come along with our A-, and instead of deprotonating the nitrogen, there's no protons on the nitrogen, we're going to deprotonate next door to this iminium functional group. And so this is where we generate our enamine. So I'm going to deprotonate here. There we go. I'll take these electrons in this HC bond and use them to attack that. It's not a carbonyl group, it's an iminium carbon. And then I push the electrons to the N+. And that's what makes the N+ happy, is eventually we're pushing the electrons to N+, so that N nitrogen is neutral. And this is how we generate our imine functional group. So our final functional group, if I can squeeze it in down below here, has a new CC double bond and an amine attached to it, and that's an enamine. Enamines are so important in enzyme mechanisms, amino acid biosynthesis mechanisms. You know, if you took a biochemistry class here like Bio 98, you would have covered a whole lot of metabolic and catabolic transformations that go through these kinds of reactions and intermediates. And I'm sure they didn't draw the arrow pushing mechanisms for you, but it's all these arrow pushing mechanisms from this chapter are super important, and chapter 20. Okay, I'm going to go ahead and stop there. Actually, I can't stop there. I have to talk about oxygen as a nucleophile before we go, because oh no, what I have to do is I have to talk about the hydrolysis of imines and enamines, because these reactions go backwards. Now, we're going to drive this reaction backwards by using an excess of water. So I told you before that, you know, in a reaction like this, if we have these 2 reactants in here and we add a catalytic acid, right, the byproduct here is going to be water. And these are reversible processes. I can take an amine and an aldehyde or a ketone and drive it to the imine. I just need to add some sort of a catalytic acid and, excuse me. Or I can take water and the imine and I can drive it the other direction. Now, we don't have to be that careful about the acid if we're hydrolyzing. You could use catalytic acetic acid. Nobody does that because it's a little bit slower than if you use catalytic HCl. That's the more common way. So if you wrote catalytic acetic acid here, that is not wrong. I'm just going to write catalytic HCl because that's the more common conditions. But again, if you just want to remember, so what is it that makes this reaction work? You're using an excess of water. How would you represent that? You could either write the word excess here, or if you write it under the arrow, that implies that it's the solvent. And if it's the solvent, it is present in excess. And you don't need to write the word excess. Writing water under the reaction arrow means it is the solvent and it is present in excess. So those are two ways to represent this. So you can make imines, you can hydrolyze imines. You can also hydrolyze enamines. You can go backwards if you have an enamine. Let's go ahead and do that. And I'll go ahead and draw it in, I'll try to make this kind of fancy here. It's not really that fancy. Let's suppose I made an imine out of this cyclic six-membered heterocycle called morpholine. That six-membered ring with the NNO is called morpholine. So this is an enamine. It's nitrogen attached to an alkene. That's an enamine. And we can hydrolyze this. And this is kind of hard to see here. It's kind of hard to see because we're going to end up generating a carbonyl group here. So that makes it hard to see. You have to practice this reaction. You could use catalytic acetic acid for this. Nobody does that. I'm going to write out the common conditions would just be catalytic HCl. And we use an excess of water to drive the equilibrium. That's not a hard equilibrium to drive because nature loves C double bond O. And if you're clever, you can see here that I added an H. There used to be one, there used to be one H atom there, and now there's two. So if you're thinking about what happened in this reaction, it's not just that you made C double bond O, it's that you added an H to a carbon atom. That's the essential feature of this reaction. Wow, can you guys see that? My screen just said, hey, low power mode, 10% battery remaining. That's pretty scary. Okay, so we end up with our amine byproduct, and that's how you hydrolyze imines and enamines. Usually once you go through the trouble of making an imine or an enamine, they're precious and you don't want to hydrolyze them that quickly before you do something with them. We're going to go ahead and stop right there. So imines and enamines, that's really the power functional group for the day. And when we come back, I'm going to come back and talk about oxygen nucleophiles.